Today we will drive a new method, general stiffness method. But when we go over the derivation, you will see that it's actually not a brand new method. We combine what we learned in the slope deflection method and the moment distribution method. And the main strength of the general stiffness method is it can handle all kinds of deformation, axial deformations and bending deformations. So in order to drive it, again, we will be using a simple structure. An example structure. So let's draw it. Let's take a continuous beam. This end is fixed. I have a pin support here, another pin support, and another pin support. So this is a 3-span continuous beam. And let's say that I have uniformly distributed load at the middle, W. So the length of this member is L1, L2, and L3. So let's put some labels. This is point A, point B, point C, and point D. Now, our starting point is, as always, we do discretization. Let's divide the structure into simpler pieces that we can better describe their behavior. So, pin support node A, member AB, node B, member BC, node C, member CD, and node D. Now let's go over the degrees of freedoms. Node A is free to rotate. That's theta A. Node B, we have rotation, theta B. Node C, we have rotation, theta C. And we know that this end is free to rotate. So I can use modified equations for member AB, and I can get rid of, or I don't need to calculate the value of rotation at A. Okay, so basically in this structure I got 2 degrees of freedom, which is theta B, or rotation at B, and rotation at C. Now let's continue. Let's continue the way we do in moment distribution method. So let me draw the structure one more time. So this is our structure. We have a uniform distributed load at the middle. So we say that this structure is equal to, all nodes are clamped as we did in the moment distribution. So let's draw the representation of it. We have the uniform distributed node. So this is the case when all nodes are clamped. Meaning that all degrees of freedom are 0. Okay. Now in that case, we can actually calculate the member end forces. So I have a member loading at member BC only. So the member loads are as follows. I have 2 end moments. Magnitudes are W L2 square over 12, W L2 square over 12, and also I have 2 shear forces. Magnitudes are W L over 2, W L over 2. So this is the case when all nodes are clamped, but remember that in moment distribution, we were releasing the nodes one by one, and we were uh, calculating the effect of the unbalanced moments. So let's draw that as a figure. Now this is our structure. So here we are saying that the node B will deform in such a way that it will generate a moment in this form, the same moment but in the opposite direction, square over 12, and I have the same moment here, WL square over 12. And I have the shear forces also. Let's show it this way. W L over 2, W L2 over 2. Okay. And the second case actually where we have only the nodal loads. Only equivalent nodes, nodal loads, and we have the case where we have only the nodal deformation. Again, let's repeat what we did. In the moment distribution method, remember that we were considering two cases. In the first case, we clamp all the nodes, and this way we were able to get all the unbalanced moments. Now here I have written it in a more general way. I clamp all the nodes. I have the unbalanced moment here, WL square over 12 due to this member load, and also I have the unbalanced shear forces. And then we said that in the moment distribution method, the structure will deform in such a way that it will balance the forces that are generated in the members due to the deformations will balance all these unbalanced forces. So it is that case actually. Here we are saying that we will have only nodal deformations here, and these nodal deformations will balance all the unbalanced forces. That's why I show all the forces in the opposite direction. And you can just think of it this way. This is our original structure. This is the original structure where we have all the forces and all the deformations. And I'm investigating that structure into two parts. The first part is where I have no deformation, only the effects of the applied member loads, plus the effect of the nodal deformation. So this case plus that case should give me whatever I have in this case. And as you see, all these forces that I show here, they cancel each other. What I'm doing is nothing but a superposition. And I'm investigating this structure into these two parts. Okay, so this is the force parts. This is the free body diagrams. So let's free body diagrams, and free body diagram in two steps. So let's take a look at the deformations now. Let's draw the deformations. Now I have 2 degrees of freedom, and I will be investigating the effects of degrees of freedoms one by one. So I will draw my structure like that. Oops, let's use black color instead. So this is the original structure here. And I got 2 degrees of freedom here, theta B and theta C. And due to that rotations, we will observe a deformation like that. I don't know how it will deform, but it should be in the opposite direction. So let's show it this way. Okay, so the way it will deform doesn't matter, but I'm just sketching it. So this is equal to, we have, let's draw the same structure, plus, plus, pin, pin. So the first case is only theta b. So how does the deformed shape will look if I have only rotation at b? So let's sketch it. So I have theta b here in the counterclockwise direction. And due to that theta b, I see a deformed shape like this. But when I say only theta b, I have to make the rotation at c equal to 0. So let's redraw it one more time. So I got the effect of theta b only, so the rest of the deformation are all equal to 0. So this is the case when we have only rotation at b, plus only rotation at c. So let's draw it, the structure one more time. So let's show the rotation at c. This is theta c. And let's sketch the deformed shape. So 0 rotation at b. And I have deformation like that. So only theta b means, let's put a note, all other degrees of freedoms are equal to 0. Likewise, all other degrees of freedoms are okay. So here we are assuming that when we have, this is the total deformation in the structure. We have theta b and theta c, and I'm doing a superposition. Again, I am saying that this deformation is equal to the combination of this one plus the combination of the second one. In the first case, we have the effect of rotation at b, the rest is equal to 0, plus the effect of rotation at c, and the rest of the degrees of freedoms are 0. So when we add the deformed shape of these two, we will obtain the deformation created by theta b and theta c. If we agree on that, I can actually rewrite that superposition, what I have just drawn here, in a different way. And remember that in our free body diagram, in the first case, all degrees of freedoms are 0, so there's no deformation here. And we said that the deformation are caused by this given unbalanced forces. So let's draw the same, combine these two and draw the same structure one more time. So I'm just drawing the only deformation case. So we have this one. This is the structure. So let's show the unbalanced forces. I have WL over 2, WL over 2, and the unbalanced moment is this way. The magnitudes are WL square over 12, WL square over 12. And due to that unbalanced forces, we expect to see a rotation at B and the rotation at C. So we are saying that this is equal to, so we will combine, we will calculate the effect of each degrees of freedom one by one. So we have only theta b. So I'll just write it this way. In order to simplify it, I just multiplied this deformation by theta b, and I'm drawing the deformed shape as follows. This rotation is equal to unity 1, and I see the rest of the deformations are equal to 0, plus I'll just write the same, draw the same structure one more time, times theta c, pin, 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 and I have a unit rotation right here, and the deformed shape will look like this. Okay, so let's repeat, but before doing that, let's isolate this part, because this part is very important. This is where we're going to get all our equilibrium equations. But let me repeat one more time. So here we say that the deformation are caused by these unbalanced forces, and the total deformation can be described by the deformation due to the first degrees of freedom, theta b, plus the deformation due to the second degrees of freedom, theta c only. If I add these two, I'll get the total deformation. So what I did here is I just combine these two graphs and rewrite it. So here we said that I have the unbalanced forces, and this theta b, or rotation at b and rotation at c, will be due to these unbalanced forces. The structure should deform in such a way that it will generate these forces. So in order to simplify the deformations, I just investigated in two pieces. In the first case, I have only theta b. So instead of writing it in this form, I further simplify it. So I have a unit deformation at b multiplied whatever the rotation I have, plus the second case I have only theta c. I have a unit deformation. I just draw the unit deformation rotation at c and multiplied it with theta c. So let's write it theta c. When we look at these two figures, actually I know what the rotation is. Here in this figure, the rotation is unity. So by using the slope deflection equations, I can calculate the end moments of this member. Plus, I have a rotation here, and the magnitude of the rotation is also unity. So again, by using the slope deflection equations, I can calculate the member end forces. When I transfer them to the nodes and add them up, they must be equal to this WL square over 12. This would be, when I do that addition in this node, I'll obtain my first equilibrium equation. I'll do the same thing for the second node. I will calculate transfer the moments due to that rotation to the node C. Do the same thing here. Add them up, and it should be equal to the second unbalanced moment. And this will give me my second equilibrium equations. I got two unknowns. I obtained two equilibrium equations, and this way I should be able to analyze this, or finalize or determine the values of these two degrees of freedoms. So let's do that. So let's write down the same free body diagram one more time. So this is the structure, node B, node C. I will not show the shear forces this time because they are directly applied to the nodes. I will just show the unbalanced moments. I have W L square over 12 here, and WL square over 12. Let's also show the degrees of freedoms. I have theta B and I have theta C here. So we say that this is equal to. So case 1, only theta B, rest is equal to 0. Now I will draw the free body diagram, so I will just draw the discrete version of the structure. Remember that whatever I have here, I will multiply it by rotation at B plus case 2 only theta c rest is equal to 0. So let's again draw the discrete version of that structure. Okay, now in the first case we have only theta b, so I have a unit rotation here, 1, 1, and rotation at c is equal to 0. In the second case, I have a unit rotation, 1, this is also 1, but at b is equal to 0. So basically, when I multiply this with theta c, I will obtain this rotation. So that's why the rotation here is in the counterclockwise direction. When I multiply this by theta b, I should obtain this rotation. I have a counterclockwise moment here. So I'm saying that in order to create that moment, rotation, I need a moment. So I'll call it K, B, B. And in order to keep this rotation equal to 0, I have to have another moment here. I'll just say this is equal to KBC. Likewise, I need a moment here. This is KCC to keep that rotation equal to 0. And I need this moment to create a unit rotation at C, and I call that moment equal to KCC. So let's draw the deformed shape due to that rotation. So this end is free to rotate. So I have this is equal to 1. And the deformed shape of the structure will be like that. That's equal to 1. Second case, 0 rotation here and unit rotation at this end. That's equal to 1. And this is equal to 1. So let's go member by member. And for each member, calculate the end moments due to the rotations. So for member AB, I have a unit rotation and the magnitude of that moment. Remember that for member AB, we will be using the modified equations. That's equal to 3 times EI divided by L1. The second member, member BC, in order to create that unit rotation, use the slope deflection equation. 2EI over L multiplied by 2 theta B gives me 4EI over L2. And in order to keep that rotation equal to 0, again use the slope deflection equations, and then this we will get 2EI over L2. Okay, transfer them to the node. Transfer it to the node, and at the end of the day, we will get KBB as equal to 3EI over L1 plus 4EI over L2, and KBC is equal to 2EI divided by L2. So these are the moments due to that will be created due to this given deformed shape. And now I will do the same thing for the second case. use the slope deflection equations and calculate the moment. So I have a unit rotation at this end. So this moment is equal to 4EI over L2, and that moment is equal to 2EI over L2, and due to that unit rotation, this moment is 4EI over L3. Transfer them to the node and determine what KCB and KCC is. So I transfer it here, here, and here. Let me do one correction. This should be KCB. Sorry for that. And then write down the nodal equilibrium equations. And from the nodal equilibrium equation, I obtain KCB as equal to 2EI over L2, and KCC is equal to 4EI over L2 plus 4EI divided by L3. So we determine all the member end forces due to these given deformed shape. We transfer them to the nodes and we find out what these moments are. Let's repeat the meaning of moments. KBB is the moment required to create a unit rotation at B, and here the KBC is the moment required to keep the rotation equal to 0 when we have a unit rotation at B. Likewise, for the second case, KCC is the moment required to create a unit rotation at C, and KCB is the moment required to keep the rotation equal to 0 at C, at B, when we have a unit rotation at C. And for these given deformed shapes, we determine all the member end forces. We can do it simply by using the slope deflection equations. And then we transfer the member end moments to the nodes, write down the nodal equilibrium equation, and this will give me the moments or the values of KBB, KBC, KCB, and KCC. Okay, now we determine all the forces that we need. Now we can write down the equilibrium equation. So the first equilibrium equation, I will write it using node B. So whatever I see here, my first equilibrium equation is as follows. I have a clockwise moment here, so minus W L square over 12 is equal to 3EI over L1 plus 4EI over L2 multiplied by theta B plus 2EI over L2 multiplied by theta C. So this is my first equilibrium equation. For the second equilibrium equation, I'll write down the force balance at node C. So the second equilibrium equation, I have a counterclockwise moment, W L2 square divided by 12 should be equal to 2EI over L2 multiplied by theta B plus 4EI over L2 plus 4EI over L3 multiplied by theta C, and that will be my second equilibrium equation. Now, as you see, we have two unknowns, theta B and theta C, and we obtain two equilibrium equations. Now, if we express these two equations in matrix form, This is what we get. So here I have 3EI over L1 plus 4EI over L2, 2EI over L2, 2EI over L2, and 4EI over L2 plus 4EI over L3. I got theta B, theta C, and that's equal to minus W L2 square over 12, W L2 square over 12. Now, we call this matrix as our stiffness matrix. And it's usually shown by the symbol K. This vector is unknown displacements or unknown degrees of freedoms, and it's usually shown by U, and this is the equivalent applied nodal loads. And it's shown by symbol F. So at the end of the day, when we analyze the structure using the stiffness method, we always get a system of equations as follows. Stiffness matrix multiplied by the unknown displacement should be equal to the equivalent nodal loads. Now, when we draw the stiffness matrix in this form, it has some properties. The first property of the stiffness matrix is it has to be symmetric. Okay, so K must be symmetrical all the time. If you are getting an unsymmetrical matrix, then you are doing something wrong. And also, remember that the physical meaning of the diagonal members, these two, is the moment required to create a unit rotation or translation. The force required to create a unit translation, moment required to create a unit rotation. So this can never be equal to, never be negative, and cannot be zero. So it has to be positive all the times. And remember, this coefficient comes from member AB. It's the contribution of member AB. It shows the resistance of member AB. The second coefficient comes from member BC. It is the resistance of members BC. And all these contributions coming from each member should be positive also. So you should never see a plus coefficient and a negative coefficient. It will never happen. Okay? So this matrix should be positive definite. All the diagonals must be positive. And when you investigate the coefficients coming from each member, these coefficients must be equal to, must be positive also. So the other property of this matrix is, oops, let's write it. So the diagonals must be positive. Okay, so when we solve this system of equations, K times U equal to F, we will determine the values of theta B and theta C, and the rest is very straightforward. You can use the slope deflection equations to determine the member end forces. Okay, now let's work on the same problem. This time I put some numbers. Span lengths are 4, 5, 4. And let's say the uniform distributed load is 10 kilonewton meters. So let's analyze this structure using the stiffness method. So we already discussed that I'll be using the modified equation for member AB. So I will have rotation at B as my first degrees of freedom and rotation at C as my second degrees of freedom. So the next step is handle or determine the equivalent nodal loads. So we will do superposition for that. So we say that that's equal to no deformation case. All degrees of freedoms are equal to 0. No deformation case. So I don't draw it this way. So let me erase this part. Or let me rewrite it, redraw it one more time. Sorry for that. We will draw the discrete version of them. So this is member AB, member BC, and member CD. 10 kilonewton per meter. So when we calculate the fixed end moments, this is equal to 20.83, and this one is equal to 20.83, and the shear forces, we don't use it, but let's calculate them. This one is 25, and this one is also equal to 25. So this is the case when all nodes are clamped, all the degrees of freedoms are equal to 0, but also we have the second case plus, where we just consider the effect of only deformation. So we name it as only deformation case. So where we show all the unbalanced forces, and here we are saying that the structure should deform in such a way that it should create the same moments, unbalanced moments, but they are in the opposite direction. 20.83, 20.83. So by looking at this figure, I can actually determine my force vector. So F, my force vector, is equal to my first degrees of freedom. Let's say that it is equal to theta 1. So I will also don't label it as theta b from now on. I will just show it as this is equal to d1, my first degrees of freedom. That's equal to d2, my second degrees of freedom. So the force corresponding to the first degrees of freedom is 20.83. So I have a counterclockwise rotation, but my force is in the clockwise direction. So this should be equal to minus 20.83. My second degrees of freedom is rotation at C, and the force corresponding to that degrees of freedom is 20.83. It's in the counterclockwise direction. They are in the same direction. So my second component of my force vector is equal to 20.83. So here I obtain my force vector by doing the superposition. So in this step we determine our force vector. So let's put a heading here, force vector. In the second step, we will determine the stiffness matrix. We already determine all the stiffness coefficients, but I will just repeat it one more time. So case 1, d1, which is our rotation, is equal to 1. d2 is equal to 0. So let's draw the free body diagram. Now I apply a moment. Magnitude, the name of that moment is K11, and this moment will create a unit rotation that's equal to 1, that's equal to 1. And then I apply a moment here. I will name it as K21, and this moment will create a 0 rotation here and 0 rotation here. So the deformed shape will look like this: member AB, member BC, and no rotation here. And then the moments, this is equal to 3EI over 4. That moment is 4EI over 5. This one is 2EI over 5, and that's it. So transfer them to the node. And from that transfer, I obtain, just write it here, K11 is equal to 1.55 EI. It is the summation of 3 over 4 EI plus 4 over 5 EI. And K21 is equal to 0.4 EI. Now let's work on the second case, case 2. D1 is equal to 0, D2 is equal to 1. Now let's draw the free body diagram one more time. Now I apply K22 this time, and K22 will create a unit rotation, so this is equal to 1, that's equal to 1, and then I will apply K12, and K12 will keep the rotation at this point equal to 0. So the deformed shape, this is will look like that. And use the slope deflection equations. So this is 4EI over 4. That moment is 4EI over 5. And this moment is 2EI over 5. Transfer it to the node and determine, write down the moment equilibrium equation at the node and determine what K12 and K22 is. So K22 is equal to 1.8 EI and K12 is equal to 0.4 EI. Okay. And you can just think of this as multiplied by theta b multiplied by theta c. And from this free body diagrams, we can obtain the stiffness coefficients that we will need for the solution. So we have the stiffness matrix, we have the force vector. Now we can solve it. So solution. Now my stiffness matrix is as follows. I have EI 1.55, 0.4, 0.4, 1.8, rotation at B, rotation at C, or we can write it as D1, D2, and that's equal to minus 20.83 and 20.83. So when we solve this system of equations, we will obtain rotation at B as equal to minus 17.427 divided by EI, and rotation at C is equal to 15.447 divided by EI. Let me write it this way in a better way. Alright, now we determine the values of the degrees of freedom, but of course the analysis doesn't end here. So we have to recover the member end forces. So there are two ways of doing that. Member end forces. As we discussed before, you can always slope deflection equation. So let's say by using slope deflection equations. So let's calculate MBC. So moment BC is equal to 2EI divided by the length multiplied by 2 theta b, 2 times minus 17.427 divided by EI plus theta c 15.447 divided by EI plus the fixed end moment, and the fixed end moment is, we already calculated here, 20.83, and this will give me a moment that's equal to 13.0.7 kilonewton meters. And if you calculate the other moment, MCB, by using the slope deflection method, you will obtain it as minus 15.47 kilonewton meters. So that's one way of doing that. But what I want to discuss here is how we can use the coefficients, what we find out in these derivation, to calculate the member end forces. So I'll just say by using stiffness coefficients. So let's take a look at it. Now let's focus on member BC. Now in this free body diagram, when we have rotation at C, the end moment here is this 4EI over 5 multiplied by theta C, and 2EI over 5 multiplied by theta C. I'm just focusing on member BC right now. plus we have the effect of theta b. So what is the effect of theta b on member BC? It's right here, if it's in these coefficients. When I multiply 4ei over 5 by theta b, I find out the moment here due to theta b. Likewise, when I multiply 2ei over 5 with theta b, I find the moment at this end. When I add the moment with this one, I calculated the moments due to the theta b and theta c. So in other words, we calculated the moments due to only deformation case, and I have to add plus the fixed moments, whatever I find at this case. So if I write everything in the as a formulation, so member end force BC is equal to the stiffness coefficients BC multiplied with the member end displacement UBC. So this is what I get from the only deformation case, plus the fixed end moment BC. This is what I get from the non-deformation case. So let's write down the stiffness coefficients. So KBC, I will just write it in matrix form. And the member end displacements are as follows. I have theta B and theta C here. This is for member BC. And the fixed end moments, I will use this free body diagram. So FBC fixed is equal to, I have a counterclockwise moment. So this is 20.83. And the clockwise moment at point C minus 20.83. Okay, so I have this part 20.83 minus 20.83. Now let's determine the stiffness coefficients. So I will use the same approach. Start from this end. So when we have the effect of theta b, it creates a moment that's equal to 4ei over 5. So I got 4 over 5 here, plus the effect of theta c, which is equal to 2ei over 5 times theta c, meaning that I have 2 over 5 here. When I want to calculate the moment at point C for member BC, I got 2ei over 5 should be multiplied by theta b. So this is 2 over 5. And I have 4ei over 5 multiplied by theta c. I got 4 over 5 here. And when you do that calculation, we determine the end moments of FBC as 13.07 minus 15.45. Of course, you can argue that what we did is exactly the same what we did here. So these are actually equivalent. The answer is yes for this specific problem. Yes, because we have only rotational degrees of freedoms here. But if you think about it, in another problem, in another case, when we have a translation of degrees of freedom, if you use that approach, you will directly get the shear forces also. And we will discuss that in our upcoming examples.